Boundary value problem example 3. So now remember, these are y of x, right? This is y of x. So from the last examples. Same ODE here. Let's start with greater than 0. If this is greater than 0, this has to be this, right? I'm gonna go through this fast. So remember, look at the overview if you want a more comprehensive view of this. Look, that's complex, right? Yeah, it is. So that's complex. I don't even need to write that down. Yeah, I should. Let's look at the first boundary condition. I'm going to kind of do this in my head, take the derivative, We can see that this first one's going to go to 0 because it's going to turn into sine. This one will stay here. We have mu cosine mu. Oh, sorry, I completely forgot the C2 there. Yep, okay. Yes, and then that's 0, such as 1. So then we can rewrite this like that. And then we can look at the second boundary condition. I'm taking the derivative again. Okay. This will be negative. So for this one here, we want to take a look at this one. We want to figure out what value of that would make it 0. So we're going to look at sine. We want this to be 0. So mu x would be, what would make sine 0? Anything of pi, right? So that'd be n pi. Oh, by the way, this should be pi, because I'm supposed to plug in pi there. That cancels. Mu is equal to n. Look at that. So that's our that's definitely an eigenvalue. We have a non-trivial. Non-trivial y, right? That's great. Now, I am suspecting something here, because if you look here, we also have this mu here, and that can be 0, but if mu is 0, then y is c1. So I believe that we're going to have a 0 eigenvalue with a constant y eigenfunction, the constant eigenfunction. I can foresee it, but that will be determined. So I can already say that there is one, but we can also probably figure that out when we do this one here. Let's just take a look. When this is 0, we have right? So then R is repeated zeros. C1 plus C2x. That we can, was it prime 0 first? Yeah. That's C2 is 0. So then we have y equals, oh, look at that. Y equals C1. See, this is exactly what I wanted. I can already see, yeah. Because look, if you take the derivative of this again, this is just going to be 0. You can't, it doesn't give you anything, so you stop right here. So, that just confirms that, because, if we look at this one here, let me write this in green. Right, if that's the case, then lambda is 0 for that case. So we have a few things going on here. So we have this one with this, and we have this one and this one, right? This just confirmed it. So now if we go down, sorry, that's confusing. I'll write out a nice chart in a second. We'll make it look nice. We have one left, and I can tell you right now that there's going to be only trivial solutions for this one, probably. And I can already know that this is just going to be this one here, because it's the only one we haven't used yet. And then y prime of 0. Well, yeah, okay, yep. We're going to be left with this right here. Right? So then y, this is just like the last one, the last problem we did. Right, just plugged in for C2 there. So now we take the derivative again. Minus, yes, perfect. Perfect, because look at this. Sorry, this should be times mu. So we can take out this. Think about this now. We have two cases. For this one here, this would lead to y being equal to 2 C2, and that once again further confirms that we have y as being a constant again when mu is 0, when that leaves us the same thing. So now we look at this one over here, and we see that this is true when mu is 0, because if mu is 0, then this becomes 0 because it's 1 minus 1. So that just leads to the same thing over here, showing that y is constant. So if we go down to here now, make a nice little chart. I'm going to make a little chart because we have more than one. it doesn't need to be that big. Okay. So we can see that when lambda sub n is 0, we have a constant y sub n. Now, whenever you have a constant y sub n, it could be any value, right? Well, just pick one. Make your life easy. It has to be non-zero, just pick one, right? It's not 0, but it's some constant. It's a non-zero constant, just pick one. Okay? I'm sorry. Actually, you know what? Actually, let's not... It could be any value, but let's not say it's 1, because we don't know that for sure. I'm getting a little ahead of myself here. There's a reason why I said it could be any value. So we're gonna call this not, because it's not like the other eigenvalue where it's gonna be some function of n, you know what I mean? It's gonna be constant there. It's gonna be outside of the series. So if you can picture later on, when we have our series, it's gonna be this plus the rest of the series stuff, right? So this is just gonna be some not term, right? Just gonna be some constant. Just call it that, C naught. That's fine. So now, the second eigenvalue, we had what over here? We had, right, so we had n, so it's just n squared, right? Because we had our mu sub n was equal to n for everyone. I completely forgot to write this. And then we also have, let me just make sure this is right. This is number 18? 16. Yes, this is correct. Okay. So now the eigenfunction, let's look at, I think it was cosine. C1 cosine, something like that. C1 cosine mu x, so C1 cosine, well, C sub n cosine n x for every n is 1, 2, 3. Okay. Now, just so you're aware, technically we could just call both of these 1. They could be, right? But I like to write it like this. Some people might say to do that, but I like to write it like this because it keeps the constants in line, and you can see later that when we do our general solution, it'll make it. I think it makes more sense to leave them like this. Just being able to understand that it could be any value is very important, in my opinion, because it doesn't matter what we put there, because when we solve for t, we're going to get another constant. And when we get that other constant, it's going to get multiplied by these values here. So then that's how the constant comes back. And then you can end up getting the constant back. But I like to just keep it here for simplicity. So let's go. That sounds like a good example. I think we have some more like this coming up. So let's take a look at those. See you in the next video.